This is a quick outline of what my talk today is going to be about. I'm going to start with a quick introduction to noise and MRI. And I know that we have a lot of experts in the room, so this is going to be pretty fast and pretty high level. After that, I'm going to give some theoretical insights and historical context to this SNR versus spatial resolution trade-off that we often have to make in MRI, and how that trade-off between noise and spatial resolution influences the way you want to do image reconstruction. After that, I'm going to show you a bunch of results in both high field and low field applications. I'm going to have some discussion on how do you judge the quality of an advanced reconstruction result, and then I'll finally wrap up with some summary. So getting right into things, the topic of my talk today is noise, and so I need to define what type of noise I'm talking about. So for the context of this presentation, I'm talking about thermal noise, also called Nyquist or Johnson-Nyquist noise, or just Johnson noise. This is the noise that exists because our bodies and the electrical circuits that we're working with are filled with charged particles, and these charged particles are thermally agitated. They're moving around randomly. That random motion of the charged particles is causing fluctuations in the circuits that are picking up our signal and giving us this random noise behavior that we observe. This is a problem in MR because NMR, the nuclear magnetic resonance phenomenon, has low sensitivity. So even if we apply a very strong magnetic field strength, the very strong B0 field, the amount of signal we get out from that is relatively small. And so this noise is problematic for that reason. This leads to an unfortunate trade-off for us between signal to noise ratio, resolution, and imaging speed, that generally we have to make some kind of compromises here. If we want one of these to be really good, we have to make compromises in either one or both of the others. And something that I think a lot of the senior people in the room may know, but which may be sort of a revelation to some of the students, noise can be very, very limiting regardless of field strength. So at this workshop, we're particularly worried about noise when it comes to low field systems, but I wanted to show you a bunch of high field examples as well, where noise can be problematic. And so the next set of images I'm going to show you, some of them are low field, some of them are high field. And if I was there in the room with you, I'd ask you to raise your hands for each one saying, do you think this is high field? Do you think this is low field? I'm not there in the room with you, so maybe you can just mentally do this to try and guess before I tell you the answer, which one of these examples is high field versus low field. So here's an example of a noisy image here. It may actually, and hopefully this comes through the Zoom okay, it may actually be unclear what exactly we're looking at given how much noise there is. This is actually a very heavily diffusion weighted image. If I turn off the diffusion weighted image, the diffusion weighting, you can see the structure of what's going on much more clearly. This is actually a mouse. And here's the brain. You can see the spinal cord, the nose, and the mouth, etc. So hopefully you have a guess in your head about whether this is a high field or low field image. Turns out that's a 14 Tesla image, still very noisy. This next example is a human image. You're looking at sagittal images of the brain. And it may be difficult to see exactly what you're looking at. There's a reference image there to help you get situated a little bit better. Again, hopefully you have a guess in your mind of whether this is low field or high field. Turns out that's a 9.4 Tesla image. The reason it looks so bad is that this is actually an oxygen 17 image. This is naturally abundant oxygen 17, which has really, really low natural abundance. It's a very hard experiment to do. This reference image I showed you, it's also a 9.4 Tesla image, and it looks bad because it's a sodium image rather than the proton images that you may be used to looking at. Here's another example where I have a series of images now And you can see that as the series progresses, we get more and more swamped with noise. This is 3 Tesla data, and we're just doing more and more diffusion weighting to the point where there's basically very little, or it looks like there's very little signal left compared to the noise that exists there. One more example here, that this is a brain image again. You can see it's quite noisy. This is data acquired at the disk center on the 0.55 Tesla system there. This is the first low field image that I've shown you, but we see the expected noise concerns with it. One more example, very noisy looking image. This is a 3 Tesla brain image. It's an axial brain image. It looks so noisy because of the extreme resolution. So this is data I got from Colin Setzenpop, who presented earlier at the workshop. This is 660 micron isotropic resolution, and very fast acquisition associated with it as well. And so it looks pretty noisy as a result. Here's an example that looks super, super noisy. It's probably hard to tell what exactly we're looking at. If I show you a reference image, you can see, oh, okay, this is a mouse brain, that the mouse has a stroke. But these images I've shown you in the center and on the right, those are very, very noisy. Turns out that's a 12 Tesla set of images. The reason these look so bad is because they're spectroscopic images. The middle image here is N-acetyl L-aspartate, or NAA. The image on the right is a lactate image. And we just have orders of magnitude lower sensitivity for these brain metabolites than we do for water, for example, which I'm showing on the image on the left. So those set of images may be something you haven't seen so much of before, because people don't usually show you their really noisy images. The really noisy images are things you hide in your file cabinet rather than showing them to everyone. Something I want to emphasize here is that these noisy images not only look ugly, but it also causes downstream problems. So for example, if I wanted to take some of those noisy images and do quantitative parameter estimation from them, if I didn't have to worry about noise, I might get a really nice, beautiful looking image like the image I'm showing here on the left. In the presence of extreme levels of noise, the quantitative parameter maps you'll get out look rather bad. And of course, this is something that we need to do something about. And this is what brings us to constrained MRI reconstruction. So constrained MRI reconstruction is basically using some kind of prior information in order to do a better job of image reconstruction that gives us better quality images. This is something that has been around for nearly 40 years at this point. And for those of you who don't know the history of it, I think it's worth knowing the history of it. Jipei Liang and I have a book chapter coming out in the near future where we do a review of the early methods in this field. But when you look at the way constrained reconstruction is used, it's mostly applied in MRI and in the modern literature. It's mostly applied to reconstruct data that is acquired below the Nyquist rate. It's used in sort of these high signal to noise ratio scenarios, and it's used for acceleration rather than to try and improve noise effects. It's important to understand that this type of approach can also be used to mitigate noise. The same constraints we use for acceleration can also be used to mitigate noise. And this has been widely done in other imaging modalities. Things like PET have used constraints to mitigate noise for a very long time. But it turns out that it's a relatively rare thing to see constraints used for noise mitigation in MR. And it's worth taking a step back and understanding the history of why that may actually be. There are many possible explanations for why this is true. Here's one possible explanation. So It's been believed for a long time that denoising involves a loss of spatial resolution. If you're going to take an image that is very noisy and do some processing to it to remove that noise, you're going to lose spatial resolution. And I've labeled this as a historical belief. Let me mention that I still believe this is true. So this is still my belief. You may see other people with different opinions. Everyone's entitled to their opinion, but I still believe this is true. Beyond that, what people thought is that if you look at denoising versus just a lower resolution acquisition, it was believed that denoising is actually something very inefficient. And here's the classical argument that is made. And here we're going to compare a low resolution acquisition versus a high resolution acquisition, where we're doing some kind of spatial smoothing to improve the signal to noise ratio. In K-space, the low resolution acquisition is just collecting data at low frequencies where we're missing the high frequency information. But with a high resolution acquisition, we're sampling every single point in K-space. There's a problem here that this low resolution acquisition is much faster to do than this high resolution acquisition. So to keep everything fair and the same, let's just do averaging of the low resolution acquisition. So we've acquired those low frequencies twice to keep everything fair. If we then take this data and look at what happens in the image domain, we'll get from the low resolution data, we'll get a low resolution image with these really big voxel sizes versus the much smaller voxel sizes we get with the high resolution acquisition. It's not hard to show if you do a little math that with this low resolution acquisition, if you're getting some SNR per pixel, well, let's call that SNR 0, then with this high resolution acquisition strategy, you'll get an SNR that's half of whatever you got with the low resolution acquisition. And then this isn't the spatial smoothing yet. Let's do spatial smoothing to match things. So let's take every pair of pixels here, every pair of voxels, and just do averaging of those two things together and end up with a low resolution image as a result. If you look at the SNR of one of those new voxels that you've obtained in this way, it turns out that you have SNR 0 divided by the square root of 2. So the ultimate conclusion from this is that this high resolution acquisition with spatial smoothing has lower SNR than if you just did the direct low resolution acquisition. And for that reason, it was thought for a very long time that if you're solving a denoising problem, it's probably because you didn't design your acquisition the right way. It would have been much better for you to just go with a lower resolution acquisition in the first place. You'd have better SNR efficiency that way. Now, it turns out that there's a problem with this argument. And the problem with the argument is that if you look at these two images, the SNR's values that we computed here, they're accurate. So this low resolution acquisition with averaging definitely has higher SNR than the high spatial resolution acquisition that was smoothed down to lower resolution. The problem with the argument, though, is that if you look at the actual resolution, like if you look at the point spread functions of these two different approaches, this approach on the right, even though if you're just counting the number of voxels, it looks like they have the same resolution, this image on the right actually has much higher resolution than the image on the left. And so this wasn't actually a fair comparison. So this image on the left definitely has higher SNR. This image on the right definitely has higher resolution. And so we can't really compare them in the way that we just compared them. It turns out that if you actually do a fair comparison, and there's a lot of detail here that I don't have time to get into, but if you actually do a fair comparison, this second strategy is actually substantially more efficient, meaning that if you have a fixed signal to noise ratio, you can get better resolution with the strategy on the right. If you have a fixed spatial resolution, you can get better signal to noise ratio with the strategy on the right. So the outcome of this is that that classical wisdom that you shouldn't be solving denoising problems, it's actually wrong. Denoising of high resolution data can be surprisingly efficient compared to a low resolution acquisition. And acquiring noisy high resolution data, not an unreasonable thing to do. And applying constrained reconstruction to these types of approaches can also be quite fruitful. That there are a number of choices that we have to make when we're trying to approach this type of problem. One is, how do we actually do denoising? One approach that's very common because it's easy is a two-step approach that you let your MR scanner do image reconstruction, and then you take the noisy image and do denoising to get a clean image out. It turns out this is a somewhat challenging denoising problem because in this process, going from k-space to the reconstructed image, the scanner has used a lot of information that it subsequently threw away. So it threw away phase information very often. It threw away sensitivity map information very often. You have to deal with things like Ricean or non-central chi noise very often. Another approach is to just do a one-step simultaneous reconstruction and denoising approach that goes directly from k-space to a reconstructed image. We've done comparisons of this, and it turns out that this second approach, you actually get substantially better results, keeping more information during the denoising process, which is not surprising at all. So you also have to think about what types of constraints to use. There are many constraints you could use for denoising, and in the interest of time, I'm going to describe this very quickly. We're going to use smoothness constraints in the examples I'm showing you here today. And these smoothness constraints are going to be designed in an edge-preserving way, leveraging the fact that if you get a sequence of images, which you often do in quantitative imaging, there's often going to be a lot of correlation between the edge structures here. There's some complicated math here that you don't need to know anything about to understand this, but one of the important features of this is that it has very controlled behavior. We can control the signal to noise ratio versus resolution trade-off very nicely. It fails gracefully, and it has a number of nice spatial resolution characteristics that it obeys. So just to show this off, here's that 14 Tesla mouse brain image we showed before. We can control how much noise variance improvement we get. And you see that the resolution loss, that there is resolution loss, but it's relatively mild. This is a good trade-off to make, especially at this middle row, the 4x noise variance improvement. We can do the same thing with our oxygen 17 data. Very nice improvement in noise. We can do this with our diffusion data. And all of a sudden we see, hey, there's actually structure there hiding below the noise floor. We can do this at low field. And yet you can see a difference in signal to noise ratio here. The difference becomes more obvious if we look at quantitative parameter maps, where that there's a clear improvement in quality there. We can do the same thing with our very high resolution diffusion data, and again, get a very nice improvement in quality. Finally, we can do the same thing with our spectroscopic imaging data. See, hey, there's actually important, useful structure in these images. It's not just pure noise, but we can actually gain insight from what we're seeing here. To quickly discuss some things, the reconstruction approach we used is effective, and importantly, it's very well characterized. We have predictable resolution versus signal to noise ratio trade-offs, and another number of other features. But something to point out is that if we compare this to alternative approaches, it actually doesn't look quite as pretty as some of the other alternative denoising approaches that exist out there. And so you may wonder, well, if my eyes are telling me to prefer this alternative approach, why should you take my word for it that our proposed approach is the right one? Well, it turns out that if you look at quantitative parameter maps, you actually get much better results with our approach. and you actually get much better sensitivity to subtle pathological features. And this is something that I think is important to keep in mind when you're looking at advanced reconstruction techniques these days, that characterization is something that's really good. But if you don't have it, you need to be careful when you're judging image reconstruction quality, because it's not necessarily the pretty image that is accurate. It's that there's a tendency for a lot of very advanced methods to hallucinate a little bit, and you can definitely have that type of thing happening here. I don't have too much time left, but I just want to quickly mention that there are many advanced constrained reconstruction methods out there today that claim that they don't lose any spatial resolution. If you see those, I would definitely encourage you to push back a little bit and ask for justification. So in my group, we've come up with some techniques that would allow you to ask this question: have I lost spatial resolution or not? And it turns out that if you use these types of tools, you'll see for our proposed denoising approach that actually there is a loss of spatial resolution. You can see that in the analysis. But for those alternative approaches that look very good, that cosmetically have very high visual quality, they're very, very problematic in terms of their ability to detect subtle features, their ability to correctly visualize small features that may be interesting to you. So to quickly wrap up, denoising problems are something that can be found at every MR field strength. Conventional wisdom says to avoid denoising situations, but I would encourage you, if you're in one of those situations, to start thinking about, hey, maybe I should go for higher resolution. Maybe it's okay for me to have a little bit higher noise in my data. Constrained reconstruction is a good way to overcome noise if you've allowed it into your data acquisition. And then for advanced image reconstruction, characterization is important. If you don't have characterization, skepticism is important. And this is not a new problem. Back many years ago when we were working on compressed sensing, I came up with this result where if you don't know what the true image looks like, you'd say, hey, that's a really nice looking image. It has high resolution features and everything. But if you compare it to the ground truth, that there's important subcortical gray matter structures that are missing from the image. And you wouldn't have known that unless you had acquired the ground truth. So important to keep in mind that seeing is not necessarily believing with some of these very advanced image reconstruction techniques. All right, so with that, I'd like to thank you for your attention, and I'm happy to take any questions.